Force of buoyancy. Do you remember the force is acting on an object that is placed on top of a table? You're right. These forces are force of gravity and normal force. Now, if I tell you that the mass of the ball is 0.625 kilograms, can you tell me the amount of each force and its total net force? With this, first we will calculate the force of gravity, that you remember is mass times gravity. The mass was given, that is 0.625 times 9.8, that is the gravity of our planet, that gives us 6.125 newtons. Now, normal force is the second one to be calculated, and because it's on a flat surface that is horizontal or perpendicular to the gravity force, so it's equal to the force of gravity. So without calculation, it will be equal to 6.125 newtons. Finally, the net force, if you remember, is the subtraction because the forces are opposite and they're in the same quadrant. So force of gravity minus normal force, it will be 6.125 minus the same number, that will give us 0 newtons. So we just proved that the ball is not moving. But what happens if we put the ball in water? You're right, force of gravity is still there and it will be the same quantity because it's the same ball. That is 6.125 newtons going down. But is there any other force? And the answer is yes. It is the buoyancy force. Buoyancy force is the upward force that we feel in objects, is produced in objects that they are submerged on a fluid, in this case water. Let's learn how to calculate it. The formula for force of buoyancy is very similar to gravity force. Back again is mass, but this time is the mass of water displaced times the gravity. Now, the mass of water displaced is the water that you need to take out to fit in the ball in that fluid. But how can we measure it? Actually, it's very easy. Just let's go back to the formula for density. Density, if you remember, is mass divided by volume. The mass is what we are looking for, so volume that is dividing passes multiplying to the other side. And we have that mass equals density times volume. Density of what? Is the water density, as we can see here below, times which volume is the volume of the object immersed in water. Time to calculate it. If you note that the water density at 25 degrees Celsius is 997.05 kilograms over cubic meter, and the ball diameter is 30 centimeters, let's calculate the force of buoyancy. First, the mass of water displaced, back again, is water density times the volume of the object immersed in water. Is the blue area that you can see on the screen of the ball in the water. Let's calculate first the volume of the object immersed. The ball, as you remember, is a sphere. The volume of a sphere is 4/3 times pi times r cubed. And because just half of it is in the water, so we will divide it by 2. Substituting in it, 4/3 is 1.33, pi is 3.14, and the radius is half of the diameter. The diameter was 30 centimeters, so the radius is 15 centimeters to the cube and divided by 2. Doing all these calculations, that will give us 7,047.34 cubic centimeters. And we will have to divide by 1,000,000 to convert it to meters cubed, and that will give us 0.007 cubic meter. Now let's go back to the formula of mass of water displaced to calculate it. Our formula, back again, water density, that is 997.05, times the volume of the object immersed in water. We just calculated and it was 0.007. The multiplication will give us 6.98 kilograms. Substituting in our formula for force of buoyancy, the mass of water displaced, 6.97, times gravity, that is 9.8. The answer, 68.4 newtons going up. Now, if the force of buoyancy is bigger than the gravity force, it is called positive buoyancy, and the object will float. If the buoyancy force is smaller than the gravity force, it is called negative buoyancy, and the object will sink. Finally, if the buoyancy force is equal to gravity force, it is called neutral buoyancy, and the object will be able to hover, in this case, in water swimming up and down. In our case, force of buoyancy 68.4 is bigger than gravity force, that is 6.13 newtons. So in this case, it's positive buoyancy, and we just proved that the ball floats. Thank you very much.